So let's learn a little bit about machine learning and deep learning. I believe you are all familiar with these things that I'm going to show right now, but still let's refresh our knowledge of machine learning. So machine learning uses data and produces a program to perform a task. It's like the opposite of what we learned before, let's say 2000 or something. We learned that if we need to write an algorithm to do a task. In this case, machine learning will do that for us. Will produce a model in the format of a program to perform a task. This is an example here, okay, showing how to classify human activities. So what we have basically is some signals coming from an accelerator or any other sensor that we use usually for collecting human activities. Okay. And before we used to have a formula or equation, but this time we only collect the data and we label it. And in MATLAB, we have for signals, we have signal labeler, and for images, we have image labeler. And in these tools, they have some automated labeling algorithms that you can use to speed up the labeling process. Okay, so the output here will be a model, okay, that will be able to classify or to find the next or to predict the value using that model that say got from training or from fitting the data to it. So it will be able in this case to predict the value from for unseen examples or features. Okay. So the first demo is radar target classification using wavelets and machine learning. The data that I'm using here is a synthetic radar targets RCS, and RCS, for those who are not familiar with this, is radar cross section. Is something that we can use to distinguish between targets or classify targets. It's like a volume that, yeah, something like this. It's shown here. This is a cylinder. Okay. So this is what does mean the RCS, radar cross section, and it's a feature, or it's let's say data that we can use to classify radar targets. Okay. And there are other methods to classify radar targets. We can maybe look at the RF signature. We can maybe look at the amplitude of these returns or echoes. But one of these um, type of data that works very well is the RCS. So what we're going to do first, we're going to generate a data. And as I said, it's synthetic. MATLAB has in its toolbox called the phased array toolbox, it has a function that generates synthetic radar targets RCS, and we're gonna extract the feature from that using the wavelet scattering. Okay, and then we will feed this data or this feature to a model, machine learning, a classical model or a classical algorithm, and we will have two classes. We'll have the class or the targets. It's like recognizing the which target we have here. This is just an example showing that the target is a cone. Okay. Maybe we can go now to MATLAB. Okay, let's go to MATLAB and see. So here we have the demos, signal, and machine learning using wavelets. This is the script. I'm using MATLAB Live Script, guys. So it's something like notebooks. I'm using it. I didn't tell you about it, but I'm using this MATLAB Live Script that you can create easily from here. Okay, Live Scripts, or maybe you can right click in the folder where you are working, and then you create a new MATLAB Live Scripts. So this is just something that I want to share with you. Let's clear the workspace and start fresh. This is the data that is generated using the function called, let me look at that function. I'll find this here. So this is the function that this is the class that I used to generate that synthetic radar RCS data. It can be found in phased array toolbox, phased array system toolbox. So this is one of the strengths of MATLAB. It allows you to generate synthetic data if you don't have real world data. Okay, so I'm going to close this and go back to the other folder, and I saved that in these files that are MATLAB files, and I'm going just to load them. Okay, I have now the data in the workspace. You can see my workspace is now populated, and I have a helper function just for plotting. Okay, for plotting, I'm plotting here in time domain the angle vs the time. Okay, this is what means. This is what does mean the RCS information. It's the angle versus time. This is how we can understand it. Understand this RCS information. And I'm going to use the wavelet scattering transform, okay, to extract the features from different signals. And these signals are in these tables: returns, RCS returns, RCS return test. Okay. Now let's create a scattering network. I'm going to use the same function that I talked about before. And this time, I will not do this batch processing and all these things because I have a small data sets and it's in a MATLAB file. So I can use the feature matrix this way also. This is another way to extract the feature. You can index to the method that you want to use for that class or that object Sn. This is the scattering network that I created here, and use the feature matrix method to extract the feature from the data, or let's say to get just here. I'm just applying this method that extract the feature matrix from the signal or from the data using this scattering wavelet scattering network. Okay, I can run this section. And here we go. I have the features here. Okay, this is the feature, the train feature. Features for different examples or signals, let's say, and they have the test features. I split the data even before applying the scattering, wavelet scattering network. And this is a good practice, by the way. So if you are willing to use the wavelet scattering for extracting the features, it's always a good idea to split the data before you extract those features. I'm just here getting the labels for the training data sets. We have some functions here that you can use, okay, for extracting the features, because here I'm not creating a data store. Otherwise, I can use many other methods to get the labels, and it's basically just the, if you have the data store, I'm just here writing to explain that there is another way. If you have the data store, you can use the you can index to the property of it called labels. This way, I believe. Yeah, so this is the way you can extract the feature from, you can extract the labels from a data store. But we don't have a data store in this case. We have just MATLAB data. We are not using it. We can use it, but we are not using it in this case because the data set is very small. We learned before that it's good to use the data store when the data is very huge. and when we have some computation and memory, let's say, stuff to look into and to take into account. So as in this case, we have a small data set. Now I'm going to train, but before that, I will use this function called template SVM, or this is actually a class, I believe, to create an object. And this is for the SVM, support vector machine. And I will use the kernel function, the polynomial, and other parameters outflow. Okay. Here I'm just creating an object. I didn't design the model. I didn't train the model. Just created an object for my SVM, and I'm using the kernel function as polynomial here in this case. So to train this, to train or to feed the data, the features that we extracted using the wavelet scattering, you can use this function feed, this feed CE COC. I can actually go to the documentation of it and see what it does exactly. So this is a function that does the fitting of multi-class models for support vector machines. So we use this usually with SVM, but okay, many other classifiers. So it's not just for the SVM. Okay. So this is the function that I'm going to use to feed my features to the SVM model. Okay. I can run it. Maybe it will take some time. Okay, we have a very good accuracy here. Even for this is only for the training. Okay, let's now use this model. Okay, this model, the trained model that we got from training for the prediction of unseen data, or for the prediction from the test set. And they have again a very good accuracy here. And before I told you guys that the data is very well prepared. This demos is just to show you how to extract the features. And we saw here that the data is very small, but we are still extracting some features from that using the wavelet scattering network. And also we are getting a very good accuracy for the validation. And here we are doing cross validation and also for testing. This is the power of using Wavelet Transform to extract the features. You will get very good features that will help you a lot with training with fitting the data or these new features to the machine learning model or deep learning model, and then it will get a very good accuracy. We can actually examine the accuracy using this confusion matrix. This is the confusion matrix. There is a function called confusion chart that you can use to plot this. Okay, it looks very. It looks fantastic here because the classification are all correct. But when you have this confusion matrix, you need to learn it this way. You need to look at the true classes and the predicted classes. Okay, so we have cylinder here. So it was all classified as cylinder. No, sorry, I need to read it this way. So cylinder as a true class was classified as a cylinder, and it was 100% accuracy. Okay. There is again another way to train these to train other classifiers, and it's called classification learning app. This is an app that you can use to train multiple classification or multiple classifiers at once, and you want to get all these details, the accuracy, the validation accuracy, the testing accuracy, this confusion matrix for the testing, for the training, and all these things, you're going to get them there. So maybe we can, and you to start this up, maybe you can get to the, you can go to where we can go. We go to machine learning and deep learning apps, okay? And there you will find the classification learner. So this is the classification learner, okay? That's we can. So this is the classification learner app. You first need to create a session, sorry, and you can do it either from the workspace or the from a file. We're gonna do it from the workspace. Okay. So you need first to select the data. Okay. I can maybe select the train datasets, and from the workspace, the train labels. Okay. And I can use some data for cross validation. So to do so, you need to go to this small panel here and select the cross validation and set the cross validation false to a value. And also from this data, I will set some data for the testing. Okay. And final step to do is just to hit the start session. And here we go. So this is our first plot that you will see. This is scatter plot. It's showing you your data. Okay. But they are also annotated. This is one class. This is a cylinder in this color, and in blue we have the coin. We can actually separate them very easily, even using just a linear regression. But here I'm trying to show you how you can do that in MATLAB, how you can train multiple models at once. Okay. So to get started, you can train all of them, all linear, or you can train all decision tree, or you can train all this discriminant analysis, and so on. So what we're gonna do, we're gonna train all the SVMs to compare. We are getting 100 accuracy, but just let's try this and see. So when we do this, usually when we the time we have less accuracy and want to improve it, so we work either on the data, but also we can change the classifier. So the classification learner allows you to train multiples. We can go now to the second one, always for signals, but this time is a different approach. We're gonna use the we're gonna use deep learning, transfer learning, okay, with the wavelet transform. So we will feed some feature, or we will feed this wavelet scattering features to a deep learning model. So let me open the scripts, and this is my live script. This is my favorite step, always clearing the workspace. And again, I'm loading the same data, okay? And also plotting, it's again the same. Here I'm just analyzing in time frequency domain by plotting the scaleogram of the two classes, cylinder and coin. What is this class? Okay, con. Okay. Here I'm just like exploring the data in this previous section, plotting in time domain, then in time frequency domain. But I'm using the wavelet for that, for the analysis. I'm using the wavelet transform, continuous wavelet transform to analyze and see how does look like the signal or the returns from these two classes. And now the image preparation or the data preparation. I have this data here, okay? What we are going to do in this section is that we will transform the signals into scalograms. And after that, we'll use these scalograms that they look like images. They look like images to train a convolutional neural network. Okay. So I can run this section. I'm calling this helper wavelet transform image. So what does this? We can go now maybe to open and we will have the data here, the full code. And as you can see, this is the folder to to where I'm going to save the scalograms or the images. Okay, and here the training set and testing set. So I'm going to do this for the training set and testing set. But if you go to the body of the code, you're gonna see that the CWT filter banks that we are using here a different a, a different function to find the scalogram. And later on, we are saving the scalograms as images. So what we are basically doing here, we are creating a new data sets of images out of signals. So we have the inputs, which is now signals, but the output of this function is scalograms that are images. Okay. Now, next, we're gonna use the image data store. Okay. This is a way again to manage the file access. Okay. And the next step is to do some transfer learning with a CNN. We can actually create a neural network or a DNN from scratch, but it's always recommended to try the transfer learning at first stage before moving to designing your own neural network. Okay. So how to do so? You need to figure out which pre-trained model you want to use. I'm using this QuizNet, which is basically just a convolutional neural network, but it was trained on very huge data sets, and the classes are very different, are not scalograms. These images are from the real world, about animals, objects, and these things. So, but it has the weight learned from that examples, those images. So I will use this. I will get some benefits from this pre-trained instead of training a neural network from scratch. I will use this pre-trained and change some few layers. Okay, and then I will train this again to fit it to my radar cross-section data. Okay, so the first thing to do is to create an object. Then if you want to visualize, you can use Deep Network Designer. You can use that to visualize, but you can use it also to edit the network. I mean, replacing layers, changing the parameter of these layers and all these things. So this is the app. I don't know if you are familiar with or not, but you can use it to do all this data, to do all this training and testing of the networks. What I did here in this case, I opened the app programmatically, and as you can see, I have in the app here, I have it already populated, and this is the layers, or this is the topology of my squeeze nets. Okay, and you can learn about some of its properties, the number of layers, 68, the number of connection, and so on. So if you don't want to zoom out, zoom in, then you can learn from the properties of it. And as I said, you can, for example, delete this and replace it with another layer, but it should be the same layer. At least should be from the same family of layers. I cannot replace this ReLU layer with a convolution layer or something like that. Okay, and after that you can export to workspace. You can export the network. We are exporting here the network, but you can also generate a code for that network. Okay, or you can analyze it to find maybe defects in the network, or any let's say, I will not say bugs, but uh, something which is not correct in your network. Now I'm modifying this. I'm creating a new layer, okay, that I will use to replace the layer 64. Okay, it's actually a L-graph squeeze, and this is the layers of my network, and uh, it's a convolutional layer. It's a 2D, and I'm replacing it with the same, with a similar, but with different parameters, as you can see here. These parameters are different. So this is what we mean by replacing. We don't replace it with a different one, but we replace it with the same category of layers, but with different properties. And then we use the function replace, and finally we will have the new set of layers. Okay, and this will be my new squeeze net, let's say. Okay, I can now set some training options here. I'm going to use this algorithm for the training, and some other values, for example, the minibus size and the execution environment, CPU or GPU. This is for accelerating. Let me run this. Okay. So here just created the training options, and after that, I can run this. And yeah, so what I'm doing now, I'm using the function train network, and the training will start. So it's showing you the progress here. Okay, showing the accuracy as well as the losses, and telling you about the training time and many other information that you can use, that you can learn from this app. This is an app. Let's say this is a window that show you the progress of the training, and you can learn about the hardware that you are using. We are using just a single CPU. That's why it's quite slow. Okay, we can actually accelerate it using a GPU. Okay, but this is for the training. So once the training is done, we're going to use this network to classify or to predict the class. Okay. We can maybe wait for that. It's almost there. Mm-hmm. And here we go. I will have now my network. This is my network, and this is just a plot of the progress of the training. I can use now the function classify and pass give it the inputs, which is now the network and the data. I want to test or classify unseen data in this case, and the accuracy is 100. It's very good accuracy. And for this, as machine learning, I can evaluate that by plotting the confusion matrix. Okay, it's just here, and it's showing that we have a very good accuracy, either for testing, either for validation or testing. Okay, so this was the second demonstration. The last demos is classifying Giemsa stained images using wavelets and machine learning. It's basically the same as the first demo, but this time we're gonna use images instead. So we have, this is the data, and we are extracting the features, then using an SVM classifier, and we will have the class in the output. Okay, let's go to MATLAB. I'm trying, guys, to show you as much as I can of the information about wavelet transform and deep learning, machine learning. Okay, so this is images. Maybe I will go straight forward to the, I will just run this section. I'm using again data store for loading and reading the images. Okay, I can split it this way. This is a function that you split the data, that you can use to split the data, and you can learn about the data using the summary function. Okay. And we have the read all. So this is a function that you read files from, that you can use to read the files from a data store. And this is the most important section. We are using the wavelet scattering network, this time the two-dimensional network, to extract the feature from images. And note that the data set is very small. We have some few examples here. Yeah, I can run it. I can create now a network, a scattering network this way. And the coefficients, can use the coefficient size to learn about the size of the coefficients. And I will run this now to extract the features using the wavelet scattering transform. It will maybe take some time. Okay, we are done. Now we have the features, and we can create an SVM model. And after that, we train it this way. That's the training. Okay, I have now the model that I can use for classification, and we have a very good classification here, given that the the data or the examples, this is for the cross validation. The images or the data is challenging a little bit. That's why the accuracy is not that good as before. Okay, and we can again plot the confusion charts. Okay, so this is for extracting feature from images using scattering features or scattering network based wavelets.